Hello everyone. This is a video on some introductory examples on linear transformations to make you understand the concept a little better. So this is the first example we solved for 7.1. So T is a linear transformation going from three-dimensional space to R3, and the image of the unit vector along the x-axis is given to be this. So like I've said before, we consider linear transformation as a function. So if I had given you image of something equals that, if I replace the variables a and b and replace them with vectors, then this little function becomes a linear transformation if I add more properties to it, properties that we have discussed already. So we'll be focused on how to solve this particular problem. So I'm given the image of the elementary vectors, the vectors of the standard basis of R3. If you recall, the standard basis for R3 is the three elementary vectors. And I'm given the image of each of these vectors under the linear transformation T. I need to find the image of the vector 2, 3, and -2. So the first thing I'll do is write the vector as a linear combination of these three. And we have a standard basis on hand, so writing this as a linear combination should not be difficult. And I got -2 times the last vector. We use the property above of linear transformation. It distributes over addition and scalar multiplication. So the image, I'm applying linear transformation, I'm applying the function value on both sides. The image of this vector will equal 2 times the image of the elementary vector, the first elementary vector, 3 times the image of the second elementary vector, plus -2 times the image of the third elementary vector, and these are all given to us right here. So the image of this vector, I'm just going to plug in the values here. The first image was 2, -1, 4. I'm going to apply matrix operations here. So we are doing the scalar multiplication. Think of it as a column matrix. It's a vector, and 1, 5, -2 plus -2 times 0, 3, 1. So do a little bit of math here. 2, 3, -2 equals, so I've got 2 times 2, 4 plus 3, I've got 7, -2 plus 8, -6, I've got, think about it, -2 plus 8, I've got 6, and -6, I got 0, 8, -6, I've got 2, -2, I've got 0. Make sure my math is right. And this is it. So what it's telling me that the linear transformation took a vector from R3, which was my domain, and it finds its image in R3, which was the codomain. And what it means, the vector 2, 3, -2 under the mapping T is mapped to 7, 0, 0. And that's it. So this is the first example. We're using the property that the linear transformation distributes over scalar and scalar multiplication and addition. We applied that property in this little example here. We will be using more complicated, we'll be solving more complicated problems later on. Let's do one more problem. So I want to find the matrix A, which represents the linear transformation. So here they have given you some formula. So they have given you some function value. Think of this to get a better grasp on it. It's just like I have a function on x and I'm applying something to it, right? 3x squared minus 4. Say, same thing here. Instead of an x, I have a vector now. That's the only difference. So we'll try to first check what are my domain and codomains. So I know that my vector is picking up my input. The input for the function, input is what goes here, is a length 2 vector. As you can see, input is from the 2-dimensional space, right? And the output is what you get when you plug in the input in the given formula of the function. Output is in R3 because this vector has 3 components. So my linear transformation is taking a vector from R2 and throwing it in R3. And we learned a rule: if your linear transformation is going from R2 to R3, then the matrix for this linear transformation will be of order 3 by 2. This means that 3 will be the number of rows, 2 will be the number of columns. And we'll do a quick refresher here. How do I find this matrix? The column of the matrix A will be the image of each vector in the standard basis of the domain. So I have my matrix A will have 2 columns because the standard basis of the domain, which is R2, has only 2 vectors, the unit vectors in the XY direction, right? So once you have found the image of L10 and the image of L01, that makes your columns. So I'm going to find the image of L10. We know how to find that. We just have to plug it in the function. And when I plug it in, so x1 is 1 and x2 is 0. Plug that in the function. What do you get? -2, right? And plug the second vector as the second column, and you got 4, 5, 0. And this right here is the matrix of my linear transformation. And you can check that this is the correct size based on what is happening with this transformation. And just on a side note, L10, I'm evaluating the transformation. When I say I'm calculating L10, I'm plugging in the values here. So this gives me a vector 9, 8, -2. Similarly, L01 gives me a vector 4, 5, 0. I'm plugging in the given function. So let's solve a different type of problem here. We did solve a similar problem on page 2, the first problem of this video. But in this case, now I have a matrix of the linear transformation instead of a function. So this is the matrix definition of a linear transformation. And you can see that it is taking a vector v and finding its image by multiplying it by a matrix A, and they have already provided the matrix here. So can you tell me what will be the order of this product? Because that's the image of V under the linear transformation T. So could you tell me what's the order? Because that will be my range or my codomain. So this matrix is, so I have a matrix A, which is of size 4 by 3, and I have a vector V, which is of size 3 by 1. So the resultant product will be of size 4 by 1. And this tells me that my linear transformation is picking a vector of size 3 as input. So my domain is R cube and is giving me an output of size 4. Codomain is R4. So, and this makes sense because the size of the linear transformation matrix should be 4 by 3. So it should work. The logic should work. Now, this question is really straightforward because I don't have to plug in any values. I just have to find matrix product because we're using this definition right here. So the image of any vector under the linear transformation is calculated by A times that vector. And what is the matrix A? They've already provided that to you. 201, 427, 103. And I multiply it by 2, 0, negative 1. And we all are champions in multiplying matrices, or use a calculator. So it will be 3 times 2, 6. And then I have 4. Minus 1, I got 3. And I have 8. Minus 7, I got 1 and negative 1. And there you go. Let's do one more example. In the above definition, we had a linear transformation given by a matrix, right? We were given the matrix of the linear transformation and we found the image of a vector. What if I give you the formula again? Now, if you recall, we did find an image. The matrix A of linear transformation L is, we found it already, right? In the previous example. So we have two options to find the image of any vectors. Option one, you just plug in the vector in the given formula as usual. So I'm plugging in x1 as negative 2 and x2 as 4, x1 as negative 2, x2 as 4, x1 as negative 2. And I will get the answer. I got negative 18 plus 16. I got negative 2. I've got negative 16 plus 20. I got 4. I got 4. This is option 1. If they give you the definition of the linear transformation like this as a formula, what if they had given you the other definition? Because you know, it is interchangeable. I could define this linear transformation for any vector like this. A times A is the matrix times that vector. And it will still give me the same answer. Can you guess? So if I do option 2, that's where I'm using the matrix definition. So that would be negative 2, 4, which should be 9, the matrix of the transformation times the given vector. And can you guess what will be the resultant matrix product? Well, if you guess -2, 4, and 4, you are correct because they're the same definition. I hope it clarifies and makes you a little bit more comfortable going back and forth between different types of linear transformations and how it works as a linear combination of vectors. And in the next video, we'll solve more problems in 7.1.